To start things off today, we're going to do a little bit of an activity. Now, if some of you were walking through the exploration station yesterday, you may have already seen a little bit of this, so you might know some of my answers. But what I'm going to share with you is something you've probably heard of, but maybe not yet fully considered all the different ways you can use it. And it is the old cloud in a bottle demonstration. So how many of you have seen clouds in a bottle before? Okay, about half, maybe a little more than half. Let me tell you that I use my cloud in a bottle demonstration in pretty much every advanced and undergraduate introductory meteorology course I teach. I have found levels of interest at all of those different kinds of classes. So I'm going to give you a little bit of an overview of different ways that you can use that. The first question I want to ask for all of you, if you can think of some of the things that go into creating clouds. What are some of the ingredients that we need, whether they're physical ingredients or if they're processes that are involved? Water vapor, absolutely. I heard that one. What was that? Pressure. What about pressure? You need to move up and down. That's right. And that plays into another process altogether. That's one way it works. I heard something else over here. What was that? Yes, cloud condensation nuclei. Absolutely. CCNs. I'm going to give you a couple of demonstrations on different ways you can do that. Anything else? Temperature raising and falling. Absolutely. This actually is where pressure comes into play. It's the pressure changes that can create temperature changes, but it's the temperature changes that are key. So let's start by making a cloud in a bottle using my non-flammable CCN source. I need to set this down in order to do it, but I'm going to work through, and then we'll talk about how it works. If you look carefully, nothing but aerosol, darn useful. Our bottle with CCN, you add just lastly the. So I like to use the old bike pump to make it loud. And it's hard to see in the bottle. So, one of the key things that I would hope that any student could get out of it is the difference between water vapor and cloud droplets. One alternate conception that a lot of students have is that clouds are made up of water vapor. There is water vapor there, but what you see is not water vapor. If it were, you'd be seeing clouds right now as you're breathing in and out. Clouds are made of liquid water or ice crystal water droplets. They have to be in the solid or liquid phase to be seen. So that's one important conception that this demonstration can make, even at the most basic level. But what about some of the other things that you can do with this demonstration? Well, the Gay-Lussac's law, also known as the pressure-temperature part of the ideal gas law. As pressure goes up, temperature goes up. As you pull the stopper out, temperature goes back down. It's very easy to test that with a simple $2 terrarium thermometer inside that bottle. They can qualitatively watch the temperature go up as they pump the pressure up, pull the stopper out, and it comes right back to where it started. I like to use, in a classroom setting, a classroom set of these and a bunch of 12-ounce Coke bottles. This is about a $3 fizz keeper that you can get at almost any grocery store. And it's essentially just a little manual pump. I have had students pump up their bottle about 150 times without having any deleterious effects. I wouldn't go for 200, and I never challenge my undergraduates anymore to see how hard they can pump it up, because they inevitably try. And I had a football player once. I won't tell you how that went. So, important graphing exercise. Have them plot the temperature change every 20 pumps. You should get a fairly linear relationship. If you want to emphasize the role of cloud condensation nuclei, get 2 bottles. Put Glade in one and nothing in the other. You will get a cloud in the one that had CCN. You won't in the other bottle. But I'll caution you, if you've ever put CCN in that bottle in the past, you may accidentally still get a cloud. So I would highly recommend you get your fresh Coke bottle, clean it out, wash it out, and use it just as your pristine bottle. And then, of course, if you have a more advanced topic, you know, in New York State at the Regents level, there's a lot of discussion of the relationship between relative humidity and temperature, and the role of saturation vapor pressure and temperature. These are things that can be qualitatively discussed with this exercise. Do you have any questions about it before I advance into talking about a few more things regarding clouds? Okay, then I'm going to leave you with one last demonstration. If you really just want to impress people with the beauty of your cloud in a bottle, now be careful that you might introduce alternate conceptions this way, but it turns out that if you use alcohol and not water, one, you don't need CCN, and two, the cloud will be far more visible. So let me demonstrate. And it's a good demonstration as long as you don't care about emphasizing the role of CCN. And the main difference is alcohol doesn't require nuclei in order to create droplets. There's more to it than that. I'm happy to discuss that during the activity part of today. My part in this is, of course, I'm a professor of meteorology at one of the state schools in New York, SUNY Oneonta. Say that 10 times fast. And one of the things that I want to spend some time with here in this first part is talking about how clouds are really one of the most accessible ways to get students involved in a pure scientific inquiry process. And by that I mean, quite simply, there's a lot of experiential learning that goes with clouds. Chances are kids are aware of clouds the minute they first go outside. They've been thinking about the different kinds of shapes, and they think about the different effects that those things have. And if you encourage that just a little bit, and then tie it in with some of the other data that's out there, it creates a really easy vehicle for students to ask scientific questions and answer them themselves. And so I'm trying to pitch the things that I'm talking about today in regards to the importance of clouds in terms of how can you use them as inquiry-based activity topics. So by all means, if you have questions, feel free to interrupt me and ask them. I can entertain a few as we're moving through. If I cut you off, it's only because I want to make sure that we have enough time for the activities. So that's my invitation to you. And then let's take a look at this first slide. It probably goes without saying with this crowd that clouds are an important part of what we call the water cycle or the hydrologic cycle. There's a lot of different ways to visualize this. I wanted to reassure you that even those of us who have PhDs and write for scientific journals are in love with drawing little cars and farms on our scientific pictures. This appeared in the Journal of Climate a few years ago. And the author is Kevin Trenberth, among others, who was one of the authors of the IPCC report in 2007. So on this particular picture, there's a lot of really interesting things you can do, especially with, I'd say, middle school and up students that are getting engaged in algebra, because all of these numbers do add up. There's two sets of numbers on here. The italicized numbers represent processes in which they move from one place to the other. The non-italicized numbers are reservoirs, places where water stays for some period of time. Now, I like this particular figure when I talk about clouds, because if you take a look at the role that clouds play and the atmosphere part of this whole diagram plays in the whole water cycle, that water, well, first of all, the fresh water on the planet is less than 1% of all of the water on the planet at any one time. Of that fresh water, only 1% of that spends time in the atmosphere. And it's only that water in the atmosphere that can fall out and produce the precipitation that becomes our drinking water, that waters our crops, that most of our society is built around. That's 1% of 1% of all of the water on the planet. Or in other words, if you go to an Olympic-sized swimming pool and that water represented all of the water on the planet, the amount of water available to make clouds would fill a Coke can. One Coke can versus the entire Michael Phelps-dominated swimming pool. That's an incredibly small amount compared to all of the water on the planet. And yet, how does that water make it to the Earth's surface? It spends time as a cloud. Clouds have another interesting phenomena related to them. Well, they've got many. As a member of the Cloud Appreciation Society, I appreciate all kinds of aspects of this. However, what if we talk about the phase change from that water vapor we can't see to the liquid water or the ice crystals we can? So think about your typical summer day thunderstorm, not the kind that would produce tornadoes, but the ones that kind of crop up, they rain for a half an hour and go away again. In just one average size of those thunderstorms, if you take all of the liquid or all of the water vapor that was converted to liquid water droplets, and you calculated the amount of latent heat energy that had to be released in that phase change, imagine you could create a system that, with 100% efficiency, captured all that energy and made it into electricity. Okay, well, first of all, we wouldn't be talking about fossil fuels anymore. And second of all, just a quick back-of-the-envelope calculation. The 3.4 million megajoules of energy that is released when you turn water vapor into the liquid water in a thunderstorm would be enough to power the entire greater San Francisco area for an hour and a half. And then if you consider the next time you go online, Google a picture of the thunderstorms at night from space and look at how many different thunderstorms there are going on the planet at any one time. This is a huge energy workhorse for our planet. All of that latent heat release is what drives the entire general circulation of the atmosphere, moving energy from the equators to the poles in the atmosphere. It's a lot of energy. And it's really impressive to think about thunderstorms in terms of that energy, as well as the cool lightning and thunder that everyone likes to focus on. All right, so here's another one of these really good algebra problem figures. This particular figure is actually the second generation of figures that was also written by Kevin Trenberth and a few of his colleagues. He works at the National Center for Atmospheric Research in Boulder, Colorado. This particular figure is actually observations of how radiative energy moves through the Earth-atmosphere system. And by radiative energy, or radiant energy, what we're talking about is starting with sunlight coming in, where that sunlight goes, some of it gets reflected off of clouds, some is reflected off of the surface, some is absorbed at the surface. The warm Earth then creates its own energy. It's infrared energy, as opposed to visible light predominantly for the sun. And that energy gets radiated up into the atmosphere, gets absorbed by greenhouse gases and re-emitted. And if you add up all of the possible fates for energy that started either as visible light from the sun or infrared energy from the Earth, all of those numbers should add up. Go across the top of the figure, the amount of sunlight in is equal to the reflected amount of sunlight out and the emitted infrared. If that were not true, Earth's atmosphere at the top would be warming. It's actually been shown that the Earth's atmosphere at the top is cooling slightly. At the Earth's surface, if you add up all of those numbers, you get that there's about an extra 1 watt per meter squared going into the Earth's surface. Now, whether or not that you believe that the observations from all these satellites is accurate to 1 watt per meter squared, if you put that aside, the natural consequence of having more energy go into the Earth's surface than it can emit is that the surface temperature should do what? It should go up. This is a first-order explanation using just this figure of why there should be warming with additional greenhouse gases. You start pumping extra energy down faster than the Earth can emit it back up. The reason why I put this figure in today's talk, and because you're not my atmospheric radiative transfer class who's working on their final exams as we speak, the reason why I put this figure up is because you see that clouds play a couple of different roles in this figure. They in part reflect sunlight out to space. They in part trap some of the Earth's infrared and emit it back to the surface. And even that latent heating we talked about plays an important role in trying to keep everything in balance. Clouds play a role in all three of those processes. Now, what I'd like to think about is a little exercise where we talk about different kinds of clouds and how they might fit into this figure. So I'm going to give you two examples, and let's see if we can work through them as a group. The first cloud I want to show you is just, I'm calling it the generic high cloud. To be a little more specific, I might say a high thin cloud. Now, thinking about how visible light from the sun would interact with these clouds and how they might interact with infrared radiation is an interesting thought experiment. Let's start with visible light. When visible light comes in from the sun, and you have a high, thin cirrus cloud, can I look straight up at that cloud right at the sun? A couple of you are kind of shaking your head. Some of you are like, I don't know if I want to answer that question. If it's thin, chances are the sun is almost as bright as if there were no clouds at all. The thin cirrus clouds let through a lot of visible light. In other words, they have very little effect on reducing the amount of sunlight that gets to the surface. With me so far? So the high thin clouds not doing a whole lot to decrease the amount of sunlight that gets to the surface. Okay, now here's something, and I'll help you with this one the first time, and then I'll put you on the spot for the next one. Any cloud, even the thin cirrus cloud, is really good at absorbing infrared. So infrared being emitted from the surface gets to that thin cirrus cloud and is absorbed. The amount of energy that then goes out to outer space is the infrared emitted by my high thin cirrus cloud. And my high thin cirrus cloud is really cold and does not emit nearly as much infrared as the Earth's surface would. So the net result in the infrared is less energy makes it to outer space because my high thin cirrus cloud was in the way. So let's put those two together. I don't reflect much sunlight, but I'm trapping extra energy, preventing the Earth from radiating as much out to space as it would otherwise. The net result is a high thin cirrus cloud has a warming effect on the atmosphere. Kind of counterintuitive, isn't it? We normally think about clouds as something that keep us cool, but a thin cirrus cloud actually warms the planet. All right, so now here's where I put you on the spot. Now we've got the marine stratocumulus layer coming in off of the ocean, keeping us fogged in for, let's say, most of the day. What does that low, thick fog cloud do to sunlight? Yep, if you heard from over there, it's going to reflect a lot of that light back up to space, preventing the Earth's surface from absorbing as much as it would otherwise. What about in the infrared? What do you think? Will they emit the same? Will they emit more energy than the surface? Will they emit less energy than the surface? Less, but not much. Yeah, it's roughly the same temperature as the surface. So if you're up in outer space, you don't really see a big difference in temperature between the cloud that's right at the surface and the surface that would be there otherwise. So we're still putting the same amount of infrared out, but we've reduced the sunlight coming into the surface. What effect do these clouds have on the climate? Less energy in, same energy out? They provide a cooling effect. So the bottom line to all of this is this. Identifying different kinds of clouds is more than just an exercise in trying to figure out what kind of fun shapes the clouds make. As climate scientists, we don't just care about how many more or less clouds we might see in the future. What we care about is what kind. If we're getting all of those high, thin clouds, that is a very different future climate than having more low clouds. Did you have a question?
I did.
Okay, so I'll answer this question as generally as I can. The question is that when we have volcanic eruptions, they often produce some of these cloud condensation nuclei. Some of them are particles, some of them are actually chemicals that work well in the atmosphere. Believe it or not, sulfuric acid is a fantastic condensation nuclei. Who knew, right? Well, some of you did. You're all nodding like, yeah, I knew that. I thought that blew my mind and when I first learned it. Okay, coming back to the question. If we have more CCN being produced, what kinds of effects should that have on the clouds? First of all, if you do produce more CCN into a cloud, generally it makes that cloud appear thicker. That's just in general, wherever that cloud happens to be. And you can actually, if you Google the word ship tracks, what you'll see is you'll find images that come up of places where clouds are thicker over the Pacific Ocean, right over top of the ship track because of all the exhaust from those ships going right into the cloud layer. It's a really cool effect. What kind of clouds will get affected more? My gut tells me it's probably high clouds more than low, simply because volcanoes are going to be ejecting things pretty high up. But that's not universally true, and I'd hate to generalize it any more than that. Yes? Yeah, so let me reiterate that very quickly. Volcanoes have a cooling effect on Earth's climate, and that's actually been well documented. What ends up happening is it's a combination of things. Part of it is increasing the thickness of clouds, which might increase how much they reflect. More of it has to do with preventing sunlight from getting to the Earth's surface. You're increasing the whole overall thickness of the atmosphere optically. And the best evidence of this is this is kind of nice. Normally with my undergrads, when I say back in 91 when Mount Pinatubo erupted, they all look at me like, you were alive then? However, you probably remember Mount Pinatubo in 1991. I'm gonna bet at least more of you do than my undergrads. If you remember, there were brilliant red sunsets for probably a good year to 18 months afterward. That's direct evidence of the additional particulate matter in the atmosphere making it harder for sunlight to get through. So you put those together, those are some of the bigger effects. There is a slight warming effect that comes from black carbon that can absorb sunlight and warm up certain layers, but overall it's cooling. Okay, so I'm going to advance just a little bit further here because we are at the time when I want to start the transition to our activities. But to summarize, whenever we talk about where rain and snow comes from, and the effect that pollution might have on that rain and snow, we care about what kinds of clouds we're looking at. If we want to talk about that heat source, moving energy from one place to the other in the Earth system, we care about clouds and which kind. If we want to talk about the climate system and radiative energy, we care about what kind of clouds. Most of what we do in climate science is not sufficient to just say, oh, there is more clouds or there are less clouds. We need to know what kind. And so whenever we train our students to go out and observe the different kinds of clouds, it is more than just an exercise in Latin. It is an exercise in trying to figure out what makes these clouds different from each other. It's a perfectly good taxonomy problem, which doesn't involve dissecting any crayfish or anything like that. I like dissecting clouds. This is fun, and you can do it anytime you're outside. So with that, we have two activities that I'm going to very briefly introduce and then explain how this is going to work. One of the activities is a very simple activity where we're going to create different types of clouds and have students, based on their observations, use cotton balls to make different kinds of clouds, and you are our students today. As we do this activity, however, I try to get yourself past thinking, wow, I remember doing this maybe in first or second grade. There are layers of wonderful scientific richness to thinking about what the defining characteristics of those different kinds of clouds are. And I would encourage you to think about how you could take that kind of activity and expand it to all the different grade levels that are represented in this room. So that's activity 1. Activity 2 is a cloud cover estimation activity. This is a really interesting sort of physiological and spatial recognition problem. Meteorologists have to estimate when they make an observation how many, depending on where you are, either eighths or tenths of the sky are covered by clouds. The trick is our brain is programmed to see dark space easier than white. So we tend to underestimate our cloud cover almost all the time. You have to figure out, using an activity using just blue and white paper, ways of developing activities for thinking about how you estimate cloud cover. Can you fill 20% of your paper with your blue paper with white paper? And more importantly, can you then turn to your neighbor and say, how many percent of the sky is covered by cloud? And one of the really interesting ideas that a teacher once told me is you can do that all the time throughout a semester and create an entire spectrum of cloud covers from one end of the room to the other, from 0 to 100%, and really train people to make that sort of estimation, which is an important scientific skill. So how we're going to do this is, I think we've got 4 tables, 2 and 2, is that correct? So I would ask you to divide yourselves up, and you can fight over which table you want to start with. We're going to give you about 15 minutes per activity. The 2 tables on the left, Susan will be doing the cloud type activity, and Deanna will be leading the cloud cover activity, and I will be wandering around to help answer questions. You get your paper in 10% increments.
Yeah. So the first.
And you divide it into 10 equal
Sometimes
spaces.
hard job, unless you're.
It does not come out on the same form. You write on your original top of the bottom and a little bit into the middle. Where are the cirrus that Todd talked about?
Half. And then you have 50-50. But then you have to put this half like this to keep tense. So kids explore that Yes,
somebody did. Okay, so the National Weather Service. Okay, so as we gather back together, I'll leave you with some closing thoughts. We gave you about 5 more minutes than I think we'd originally planned, and that was good time. It's going to cut down on my reporting out period, but hopefully you had a chance to think a little bit about how those activities can apply to a number of different classroom settings. What I found is that even these relatively straightforward and simple activities have a number of different ways in which you can differentiate the instruction. Depending on what it is you're trying to do, whether you're developing simple mathematical skills like fractions, whether you're trying to develop students' observational ability, and whether or not they really understand the important differences between the different kinds of clouds, and then being able to relate those different kinds of clouds to some of the things that we discussed. There's a lot you can do with those activities. Okay, so as we're gathering back together then, what I would like to talk about now is a few of the ways in which you can use or extend from these activities that we just discussed and worked through into actually using some of the NASA mission data. And we're going to talk you through about 3 different programs. I'm going to start with the one I work for because I have the microphone. And I'm hopefully buying a little time for my colleagues to clean up a little bit, and then I'll turn it over to Susan, who will talk about the other two programs. I am, in addition to being a professor, the education and outreach lead for the NASA CloudSAT mission. I'm not going to go into the whole song and dance about this. I'll just sing a few bars. But CloudSAT is a unique satellite instrument in that it is a spaceborne cloud radar. So much like the weather radars that you may be familiar with looking at the Weather Channel, they're looking for raindrops. We're looking for cloud droplets, which are 100 to 1,000 times smaller. And when we're doing that analysis, what we're essentially doing is sending energy down from our satellite into the clouds and getting a profile of where water is in those clouds. And so the main point here is that with CloudSat, and it's been flying since 2006, with a brief period here over the last few months when it was a little bit sick, but we got it back working again. We have been monitoring the global cycle of clouds and have learned some really fantastic things, such as some incredible detail into the structure of hurricanes. The expert on that is Natalie, who's in the back room. Did her entire, was it your master's thesis? Yeah, was looking at the structure of hurricanes with CloudSat. We've learned how often clouds produce rain, which actually turned out to be twice as often as we originally thought. A little bit of a tweak we now have to make to most of our global climate and forecasting models. So we've learned a lot of really interesting science. The real key piece with CloudSat, before I get into too much depth, is that CloudSat is measuring water content. And we use a scale very similar to that of a weather radar. So how many of you noticed a few of these back on the tables when you were working on the activities? I deliberately did not talk about these ahead of time. I was curious if you would pick them up and look at them and try to figure out what was going on. So what is going on in this particular kind of image? What did you think you were looking at? Okay, so this one's a hurricane. Congratulations. Actually, no, this one is a hurricane. I had some typhoons back there too, but that would have been mean for me to yell at you for. So what about this thing down here in the bottom? Okay, so it's a cross-section. You can kind of see in the upper picture where that cross-section was taken. And one of the interesting things about this is that right near the center of this particular storm, and of course you didn't all have this one to look at. I'm not really quizzing you on it. But you can see things like with this hurricane, how the eye is not necessarily vertical. And that the eye wall marks the tallest thunderstorms in the entire system. Something else you may have noticed if you had a picture like this. The clouds that are producing the rain in the spiral bands of this hurricane are not visible all the way from outer space. They are often underneath other clouds. There's usually more than one cloud out there in the spiral bands. So when you look at a picture like this one on the top, you're seeing the tops of the topmost cloud layer. The ones that are actually producing the rain are hidden. CloudSat can see them because it's got a radar that can penetrate the top cloud and into the bottom one. Now, these are fairly accessible. They're called quick looks, these particular activities. And there are two different ways that you can find them. I have put a handout in, I think, your binders. I sent that to Roberta and her assistants a few weeks ago. You can go onto the CloudSat webpage and look in one of two places. If you want to go find a quick look for a particular event, I've given you step-by-step instructions on how to do that. If what you're really interested in is some of these really interesting events with a little explanation to go with them, we have a news feed that Natalie has spent a long time putting together. And in that, you can click on an event and see both a traditional satellite image and the CloudSat satellite image with the path laid across it. So there's probably 20 or 30 that I can think of off the top of my head, complete case studies that you can download and use as discussions about how clouds look from the top and when you look down through them. If we had an extra hour or so, we could go through an entire activity where we were using those to talk about different kinds of data. But the thing that I'll leave you with is one really interesting inquiry approach is to just give students data and see what they make of it without any preamble. I just gave you those data. I didn't tell you what was in there. And many of you picked up a couple of the key features of those particular plots. It is on.
Hello again, everyone. Todd was talking about data, and one of the ways that we approach students about data is to say, when you walk into a room and you look at something, are you collecting data? When you walked in and you looked around at the table, what did you start thinking? I need a place to sit. There's stuff all over here. They're going to give me free stuff. Oh boy, I'm happy. So the data is information. Now, unfortunately for students, if you say data, it's like the window shade comes down and they go, oh, this is not math. I hate math. Don't make me do math. So one of the ways that, as Todd mentioned, to get the students into not even realizing they're doing data is to give them the image ahead of time and say, you are a scientist. This is an important piece of information that we've collected. We need your input. You're the scientist. There is your table. See what you can find out about this image. And of course they'll go, what do you want us to say? So it doesn't what you say. What do you think about it? So you can use, for example, cloud data in your science class and make it as mathematical as you want. As we found, you can use art and start introducing cloud data. Is there a difference between collecting the data and using the data? Some examples of collecting the data or gathering the data could be the students. The students go outside and they look at clouds, for example. If we can't fly them out of Earth's atmosphere, which sometimes we're tempted to do, we have to rely on satellites to do that seeing and sensing for us. And what is that called? This starts with R and ends with mote. Remote sensing. All right. So if we can't go out and touch things, we have to send satellites out there to touch things and see things and collect data. Once the data is collected, what do we do with it? Sometimes the students will scribble it on their hands. Sometimes they'll forget it totally, but somewhere in there you'll say, now you have to write it down. Oh, I'll remember it. So the data is stored somewhere. So when you walked in the room today and you looked around, you were picking up information and your level of anxiety was probably decreasing because, oh, I recognize this is a familiar sight here. Tables and teachers, I'm happy, I've got free stuff. So you were storing that data. As you do your evaluation, you are recording data. Then we're going to use the data. The students can use the data. Scientists use the data. We've collected it. We've put it somewhere until we get around to using it. It may be immediately or it may be years from now. But the data will be used. So cloud data is one little tiny part of atmospheric data that can be used to inspire your students. All right, sometimes the students can make the observations and use the data within the same project or research paper. The example here, Todd mentioned CloudSAT. I think Deanna was talking about Globe, and I wanted to give you a little bit of information about school. There's another project with which I work called My NASA Data, which houses over 100 different data sets that your students can access to look at atmospheric data. Now, they don't collect the data. The satellites collected the data. The instrumentation on the satellite collected the data. But it is available for student use.
This is how CloudSAT works. See, radar. I have a couple of these slides available. I've given them to Roberta. We don't have time to go through all of them. However, I will point out this one. This is, if any of you teach about the structure of different cold fronts and warm fronts, we had an entire article about the structure of clouds and how they relate to the old Norwegian cyclone model from 1922, which lay out how clouds work in different ways. And actually is where the term front came from, because they did the research during World War I. So these slides are available, and this is actually on the NASA Earth Observatory called Cold Front, Warm Front. And I'll leave that for you as I advance to Susan's slides.
One of the projects that is interesting for students is called the NASA Series School Project. And again, in the interest of time, I'll kind of zip through this. But the students go outside, observe clouds, come back in, send the information in to us at the data center at NASA Langley Research Center, and that data is actually used to do scientific research. The students are reporting data to help validate data collected by the Series instrument. So that is, they are the collectors, but they are helping validate the remote sensing collectors. Also, at the Share-a-thon, in case you feel cheated because you're not getting to know how to get your kids involved, at the first Share-a-thon, we will be there with additional information about both of the projects that I'm mentioning, so you can get additional information about how to participate. But the Series project is determining the effect of clouds on Earth's radiation budget. And as I mentioned, you will receive, you'll get a copy of the radiation budget at the Share-a-thon. If you would like to register for school, you just go to the school website, which is on the materials in your folder, and click on register, and then you will be sent the overpass time as to when the best time is for you to observe. We would like for you to observe either 15 minutes before or after an overpass. Then, getting back to that using the data, if your students, because of schedule, are able to observe when the satellite's passing over, you get an email that says you have a match. And you're sent a graphic where your students can look at what their observations told about clouds and what the satellite said about the cloud for the same time period. So they can compare what they have. So they would choose a satellite. You also get an opportunity to compare, contrast, and make comments. You can also look at the satellite image, the bigger picture. So if the students wanted to see where they are in the big picture of a weather pattern, they can do that. So the MODIS image is over the same general area over which their school would be located. Now, we are coming out with a different version that does have latitude and longitude. It's going to be geo-referenced. So that'll be easier for you to find your school on that one. Here you'd need an atlas to kind of figure out where you are. So then the students classify, and they have an opportunity to put down free response comments. The second project is My NASA Data. The My NASA Data project is a project that provides visualization tools for archive data. So the satellite data is archived in a live access server, which the students can access. That's what the page looks like. And again, at the Share-a-thon, we have 2 people from the NESTA data team who are going to demonstrate this for you at the Share-a-thon. So you would choose atmosphere, clouds. I would like to know about cloud cover, and I'd like to know about the monthly cloud cover. And then I get an image. Now that seems a lot of hand waving, but it's almost that easy. You choose a date and a place and what kind of cloud you'd like, and there's a visualization. This happens to be for January 1994, I believe it is. Yeah, January 1994. And then, of course, the color scale. The students, you have a lot of opportunity for some inquiry, best practices discussion there.
Thanks, Susan. And we went right up to 11:30. So thank you very much for your questions and your time. I'm sure I'm going to hang around for a few minutes, as will my colleagues. So now I guess it's time to give it back to Missy, and she'll tell you what's coming next.